4.5 months, and I'm going to just say that this is 140th day since Russia invaded Ukraine. As you may or may not know, I'm ethnically Russian, and this has been a devastating event for me, for my family. I don't have, like all of my friends are Ukrainian, you know, and so we're actively going to all the anti-war events, going to volunteering and things like that. So I ask you to please help if you can. So there's a good, so this is a link to a really good like fund in Ukraine. So maybe you know someone who's happy to who would like to help out. Please do so. Alternatively, if you would like to know more about various protest events, there's a lot of events happening in Toronto in support of Ukraine. Occasionally there's something in KW, but not recently. So, or maybe you know someone who would like to, I don't know, host a Ukrainian refugee. I don't know. You have ties, you have connections. So let me know, because I can direct you to people who know how to help. Okay. So yeah, let's not forget about people dying over there. All right. Now I'm gonna stop talking about sad things and hopefully talk about not boring things, math. There's gonna be two parts to this talk, okay? So there's gonna be a math part and a CS part. So I have, my PhD is in pure math, but my master's is actually in computational number theory. So it's an intersection of math and fascinating computer science, which I hope that I can share some fascination with you today about the stuff that I'm doing, especially because there's actually we're actively doing some research on this right now. So that's quite great. So let's start with something. So it's going to take me some time until I make the setup. So let's take it slow. We have an hour and a half, so it's better not. I think it's better not to rush. So ask me questions. I want you to remember at least part of that stuff, because there's going to be lots of definitions eventually, lots of some exercises as well. You know, so it's very important that until when I get to the definition of a class number, we really understand what that is. That sort of thing. So let's start with something very basic. We're going to recall the definition of a prime. Okay, an integer p larger than 1 is called prime if and only if the only positive divisors of p are 1 and p itself. Okay, so let's recall some examples. Examples of primes. Examples of primes. 2, 3, 5, 7, 11, 13, 19, 20, 19, 23, 29, 31, 37, 41, 43, 47, and so on, right? So there's infinitely many of them and so on, give me, so now for non-examples of primes. 4. Can you explain to me why 4 is not a prime?
Because it has 2 as a divisor, and that's not 1 or 4.
Exactly. So yeah, that's right. And so here's a fascinating thing that you've learned in school. The fundamental theorem of arithmetic. You've also seen it in Math 135, if you do Math 135, or in Math 145. The theorem goes like this. Every integer n larger than 1 can be written uniquely up to a permutation as a product of primes. Uniquely up to a permutation. So what does this mean, right? So let's just recall what this means. So if I take number like 60, okay, and so I can write it as, of course, as 2 times 30. Then I can continue factoring, and it's 2 times 2 times 15, and then it's 2 times 2 times 3 times 5, and lo and behold, right? This is product of primes. And when I say up to a permutation, what do I mean? I mean I can permute primes, and it's still going to be the same number, right? So up to a permutation, I can permute as much as I want, but up to a permutation, this is unique. Nothing else you can do, right? There's only one way to write 60 as a product of primes up to a permutation. Okay, cool. So hope everyone remembers that. So I showed you an example. Let's take a look at, so what I'm going to try to do is I'm going to try to generalize the fundamental theorem of arithmetic further. I'm going to generalize it to other interesting mathematical objects, not just the integers, but something beyond integers. That's the idea here. So we're going to start with the definition of a square-free number. A non-zero integer n is called square-free if the only perfect square that divides n is 1. Give me an example of a square-free number based on that definition. 6 is a good example, right? The only perfect square that divides 6 is 1. Everyone agrees? Okay, give me another one.
All the primes.
the primes is a good example, right? Exactly. So 7, negative 7 is also a square free number. Okay, so we understand what square free numbers are. That's good. So let's give me some non-example of a square free number.
4.
4, because 4 divides it, right? It's a perfect square. 4 is a perfect square and divides 4. 12 is another one, right? Because 4 divides it. 18 is another one because 9 divides 18. So there you go. So these are square free numbers. So what I'm going to do is I'm going to introduce this peculiar definition. Hopefully you've seen it before. If not, no worries, because we're gonna play around with it a little bit. So we're going to define a so-called quadratic ring. So I'm going to take a d, a square free integer not equal to plus or minus 1. Okay? So square free integer not equal to plus minus 1. Okay? And I'm going to define a quadratic ring. So I'm going to denote it as O sub d in 2 different ways. When d is congruent to 3, 1, 4, it's just going to be this. It's the set of all numbers of the form a plus b root d. So you can already see that if I would take something like d equals to 3, it would be the set a plus b root 3 for all a's and b's. And when d is congruent to 1, 1, 4, it's slightly more complicated, but it's not too bad. It's 1 plus root d over 2. So if I would take d equals 5, so this would be a golden ratio, 1 plus root 5 over 2, okay? Right? It will be the set of all numbers of the form a plus b times the golden ratio, varying over all integers a and b, okay? So when d is larger than 0, you see that we say that that this quadratic ring is real, and when it's less than 0, it's imaginary, okay? Because when it's less than 0, then you basically have complex numbers inside it, right? So there you go, okay? More or less clear in the definitions. Let's see an example. Some examples of the most famous quadratic rings. Hopefully you've seen some of them in some of your courses. Here's the one, very famous. One of the simplest things that you can do is you can take d equals to negative 1. Okay? Oh, yeah. Yes, I should have said that d is not equal to 1, not minus 1. So minus 1 is allowed. Sorry, my bad. Minus 1 is allowed. Totally allowed. If d cannot be 1. So I'll fix that when I'll send off the slide. So when d is negative 1, we're getting the set of all Gaussian integers. Okay, a plus b times I, ab varies over the integers. And here's an interesting thing to note about this set. If you add 2 Gaussian integers together, you get a Gaussian integer. If you subtract one Gaussian integer from the other, you again get a Gaussian integer. And when you are multiplying them, you're still getting a Gaussian integer. Do I need to convince people that this is the case? Can we see that? Tell me if you want me to show you this, because I think that this is an important result, right? So you can see how when you're multiplying a plus bi by c plus di, you multiply things out, I squared appears, and then you replace I squared with negative 1, exactly, right? I squared is equal to negative 1. So that's how it works, okay? So this is an example of a commutative ring. Okay, so I'll talk about commutative rings in a moment, okay? So let's take a look at another example. D equals to negative 3. And this is less familiar to people, but still a really cool object. It's called the ring of Eisenstein integers, okay? And it's a plus b times omega. Omega here is the so-called third root of unity, if you recognize that term, okay? So it's the third root of unity, meaning that if you take it to the power of 3, you get 1. That's the beauty of this magical number omega here. Okay, and once again it's a really simple set. So a plus b times omega, you're varying over all a's and b's. That's it. When you multiply things out this time, you notice that what you need to do, in the case of Gaussian integers, you replaced I squared with negative 1. In this situation, you're replacing omega squared with negative omega minus 1, and you can check that you're still getting closure under multiplication. A fancy term here, right? So again, sum difference product of 2 Eisenstein integers is an Eisenstein integer. Okay, that's why I defined things the way I defined it, right? I wanted this nice closure property. Okay, so so it turns out that the fundamental theorem of arithmetic does hold for both the Gaussian integers and the Eisenstein integers. Okay, but I need to explain to you how, right? I mean, so before, remember. In order to explain to you what the fundamental theorem of arithmetic is, I need to tell you what primes are, right? I did not yet define what primes are, so I need to. So we're going to spend some time defining this, introducing this definition. Now, I'm just going to quickly mention that these are examples of commutative rings. Commutative rings are basically sets that contain number 1 in them, okay, very importantly, contain number 1. You have two operations defined, addition and multiplication, in a very sort of obvious, in this situation, it's in a more or less obvious way. And both of these, so these sets are closed under addition, closed under multiplication, and both operations are commutative. Okay, so that's essentially what commutative rings are. Okay, so I'll be mentioning it really because the theory that I'm going to go for, it really applies to all commutative rings. Okay, in many ways. I'm going to emphasize when it's not. But when you think about, like, when I'm showing you, like, oh, this is an abstract commutative ring, you can think either of the integers. Integers are an obvious commutative ring. Or you can think of Gaussian integers, or you can think of Einstein integers, okay? Or something like that. Okay, cool. Are you still not, like, falling asleep? Not? Okay? Okay, you can still keep your attention. All right. Good. Let's move on. So again, we're moving towards understanding what the fundamental theorem of arithmetic is in Gaussian integers and in Eisenstein integers. So here's the first definition that we need to know. We say that an element U in a commutative ring R is a unit, okay? Is a unit if and only if it divides number 1. What is the definition of division? You probably already forgotten since you've taken Math 35, but I'll remind you. It means that you can find another element in the ring, W, such that the product of U and W is 1. Notice that this makes W a unit as well, right? So this is the definition of a unit. Now, let's practice this. Okay. It's really not that sophisticated. In integers, Z, what numbers divide 1? 1 and minus 1. Those are the only units in Z. Okay, increasing the level of sophistication. What are the units in Zi, the Gaussian integers? What Gaussian integers divide 1? Go ahead.
Plus or minus 1, plus or minus I.
Plus or minus 1, plus or minus I. Convince yourself that these are the only ones. Plus minus 1, plus minus I. Those are the only units in Zi. There's only 4 of them. Okay? And this is actually one of the exercises. You're going to do it yourself. In Eisenstein integers, there's 6 units. And actually, this is a very special situation. So it turns out that when d is less than 0, you're always going to have only units plus minus 1, except for Gaussian integers and Eisenstein integers. So those are really, really special. Really special. Okay? But in this situation, yeah, you have 6 units, so which is a lot. Okay? All right, so we understand what a unit is. Now I can introduce you the definition of a prime. Here it is. Okay, let's focus. A non-unit, so a prime. You take a non-unit element P in a commutative ring, and you write your element P as a product of 2 things. P is V times W. Okay, P is V times W. Your conclusion then is the following. You can say that, oh, V is a unit or W is a unit. One of the two. One of these two must be a unit. Okay? Who's confused? Raise your hand. Don't be afraid. Don't be afraid. We're only going to judge you once, and then you're going to leave. All right. So, it's actually not that bad. And you'll see that the definition of prime numbers that we have been using for, like, since ancient Greeks is incorrect, because this is a more proper definition. Let me convince you why. Let's take a look at number 5, okay, in integers, all right? We know that 5 is prime, so I'm going to convince you that 5 is prime with respect to this definition. I'm going to write my 5 as a product of 2 numbers, two other integers. What are they? V and W I used, okay, V times W. Okay. Can you tell me for sure that V is a unit? What are the units in Z? Plus minus 1, right? Can you decisively conclude that if this equation holds, either V or W must be plus minus 1? You believe me? Okay. There you go. Okay. Right? One of these two must be plus minus 1, because if not, right? I mean, think about it. It has to be at least 2 in absolute value, right? And it just doesn't work out, right? It doesn't work out. Yep. So that's the thing, the analogy that you should be thinking of. And now here's why the definition of prime numbers that we've been using for thousands of years is, while incorrect, we're still going to keep using it. It's because -5 is also a prime, right? I hope you believe me. Sorry, I'm just gonna. Apparently, I need to keep track that my computer doesn't fall asleep. Okay, there we go. Okay, -5 is also a prime. Okay, I hope everyone can see this. So, if we generalize this theory properly, one thing that we need to notice is that really we care about primes up to multiplication by a unit. That's the thing. So, for example, in Gaussian integers, if you can prove that 2 plus I is a prime. But really, when you say that it's a prime, what you really mean is that 2 plus I is a prime, minus 2 plus I is a prime, I times 2 plus I is a prime, and minus I times 2 plus I. So they're kind of come in a bundle, right? They kind of come together. So it's a prime, but really up to multiplication by a unit, okay? So there you go. So that's the definition of a prime. So, and what is a unique factorization domain? Okay, fancy terminology. We say that a ring is a unique factorization domain if every non-unit element can be written as a product of primes uniquely up to multiplication. Unique up to permutation, unique up to permutation, and maybe multiplication by units as well. Like, I mean, units, they're kind of, who cares about that, right? Again, so that's what the unique factorization domain is, okay? Again, every non-unit element can be written as a product of primes, uniquely, after permutation, and maybe you can multiply by units somewhere as well, okay? Are we good? All right. All right, so here's a really cool theorem called Stark-Hebner theorem. And there's also another sort of way of proving this theorem that was proposed by my academic grandfather, Alan Baker. So the imaginary quadratic ring is a unique factorization domain if and only if D is one of these 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. That's it. That's the only time you have unique factorization domain. You don't have unique factorization domain for all other D less than 0. Okay? In particular, recognize that -1 is the ring of Gaussian integers, -3 ring of Eisenstein integers. There you go. Okay? And it turns out it's much. There are a few other interesting rings that you can look at. So for these rings, you can actually have the proper fundamental theorem of arithmetic, but it fails everywhere else. Okay? Fails everywhere else. Okay? Oh, by the way, so you may be asking me, like, what is? You may be wondering, okay, so why are you focusing on negative numbers? It's because when D is positive, the problem of analyzing these quadratic rings becomes significantly harder. And here's the reason. When D is larger than 0, you have infinitely many units in your ring. Whereas when D is less than 0, you always have finitely many, right? You saw 4, you saw 6, you saw 2, you know? But when D is positive, there's actually infinitely many. And that makes things very complicated, okay? So there's lots of open problems to work in that area. So I'm going to be primarily focusing on D less than 0, okay? Because it's so much easier to analyze. Okay? All right. So let's take a look at some exercises. All right. So we have some. So I'm not sure you can give people the handouts. There's no really place for them to write there. But if they want to have them, you know, just keep them. I don't know, like in a frame. You know, I've been to Anton's lecture or something like that. Like remembering them after 50 years, telling about this to their grandchildren and things like that. So you can take the handouts if you wish. But really, exercises are right there. So I'm going to leave you with just a few moments to think about these. So exercise 1, show that omega is a unit. Exercise 2, show that 2 plus I so that 2 plus I is prime in Zi. And exercise 3, knowing that 2, 3, 1 plus root minus 5 and 1 minus root minus 5 are all primes in Z root negative 5, prove that unique factorization fails in Z root negative 5. Okay, so maybe I'll give you like what, 10 minutes to think about this? Maybe 8 minutes.
If you guys are working groups,
Yeah, so if you can discuss this, go ahead. I'll put on my mask so that I don't bother people. If you need my like help or something like that, you can raise your hand or yes, go ahead. Yeah, I can show you there. So let me show you. So it's a deep theorem.
We need to have like paper, not paper.
I have it. So it's really interesting. So let's take a look at one example and then we'll start with the thing. Take Z root 2. So here's a fact. 1 plus root 2 is a unit. Why? Let's see. Because if you multiply by root 2 minus 1. Okay? You're getting it? These are so 1 plus root 2 is a unit. Okay? Now here's the problem. If I raise it now to the power of k, no matter what integer k I take, it's going to be a different unit. And that's not true for what we've been doing, right? Yeah. So that's the reason. And it happens, and the amazing thing is that it happens in every single square root you are in one. In every single one you can find it. It's actually you can. So basically, what is happening here is you can define like each of these things. They come with a norm map. Okay. So a norm map is when you multiply a number by its conjugate. So you're saying that, say, the norm of a plus b root d is a squared minus db squared. Okay, like that. That's the norm. Okay. So here's the fact.
that's just.
U is a unit. If and only if its norm is plus minus 1. Just a fact. Because you can kind of see that you can factor this thing as a plus b root d times a minus b root d, right? You see what I'm doing? I'm multiplying by a conjugate. That's what I'm doing. Okay, so you do this, and then what's happening? So the thing is that when you're looking at this sort of equation, plus minus 1, it has infinitely many solutions. It's called Pell's equation. That's what it is. Pell's equation. It's infinitely many solutions. But if I'm going to give you the same thing, if I'm going to take a negative number here now, like in Zi, it becomes, look what it becomes. It becomes a squared plus b squared equals to 1, or plus minus 1, but minus 1 is impossible. And in Z omega, I think it becomes something like a squared minus ab plus b squared equals to 1, which is always positive as well. So this has only, and if I'm going to take arbitrary Z, let's say root negative n is positive, right? It's going to be a squared plus n b squared equals to 1. And you can see that these are all positive, right? There's always only finitely many options that you have. See it? Like this is a very obvious example, right? Right? So, because as soon as you take, say, a equals a, let's say, larger than 2 in absolute value, there you go. It just breaks. So, yeah. Yeah, absolutely. So you can just open Wikipedia and
However you
just
write
think about it. It's an exciting thing.
Okay. Exercise 1.
I know, I just think it sounds cool, but I didn't even bring a pencil. Honestly, I don't think I can. I don't know if I should finish the exercise.
That's right. That's exactly it. I mean, technically it's a bit harder.
You could do math before you go.
Dude, I haven't done math before, but I
Okay,
mean, like.
suppose that there is an MTA, it holds. Then these two factorizations are the same computation multiplication by unit.
Done math.
So 2 must equal to one of these two numbers. Exactly. So you need to know what the units are before you can conclude that MTA doesn't hold. So
That has to be.
but essentially that's exactly.
Oh, like,
I didn't think I what?
Okay. I will admit that I don't remember how to do exercise 2 without introducing the norms. I may cheat in my solution. You work, you don't listen to me. I'm just gonna work through exercise 2 on my own.
okay, yeah.
The point is,
Yeah. It's
just multiply them out.
okay. One is F is 0. So,
This is what are you doing, dude? 148.
I don't know.
Very similar.
Okay, so no, if you're gonna give 1 has to be 0 and you need to say right? Because AG plus BC is equal to negative. Wait, is this positive? No, it's not positive. Yeah. What? Yeah.
Okay.
So if you try to solve this system in exercise 2 using Wolfram alpha, I won't judge you.
Okay, well, we're given that.
Yeah.
In this case,
plus BI or C plus J, one of them has to be. We know what the units are.
Oh.
So we can check that.
Oh, wait.
Has where.
Just show A plus BI again.
Huh?
Yeah, I have that too.
Yeah,
And
that should be positive.
Wait,
Yeah,
what?
that should.
A squared plus B squared divides 2. Yes.
Yes.
2 is B. Could you please show the slide where you define ring?
Define what?
Ring.
Yeah. So I went really briefly through it. To be like the definition is a bit more subtle. There's like 6 axioms that ring must satisfy. Commutativity, associativity, distributivity, existence of an additive inverse, existence of multiplicative inverse, then I'm blinking, oh, and associative, maybe did I mention associative? Yeah, something like that, there's like 6 of them. Oh, and existence of an inverse element as well. There you go, that's the one. So that's, yeah. If you're interested more in ring theory, there is a fascinating textbook by Atiyah and McDonald called Computative Algebra, and we have a really fascinating course on computative algebra offered at the Pure Math department. So, okay, so friends, should we begin the discussion? Okay, let's go. Let's start with exercise 1. Who has a solution? Sure. Yay.
So you notice that 1 is minus omega squared minus omega. When you expand this, you will get a omega plus b omega squared is minus omega squared. So a and b are minus 1.
Exactly. So notice. So we know that omega satisfies this equation. Okay. Notice that 1 is equal to minus omega squared. But that's the same thing as omega times minus 1 minus omega. That's it. Definition is satisfied, right? This object over here is in z omega. So by definition, I just found you an element w such that omega times w is equal to 1. There you go. Therefore, omega is a unit. Okay? So, see, not a rocket science. Okay? Just computer to bring. Anyways, let's move on with exercise 2. Okay, so for exercise 2, you need to prove that 2 plus I is prime. There is you recognize that what you need to do is you need to write it as a product of 2 Gaussian integers, multiply things out, equate, and you get a system of 2 equations. Your goal is to show that eventually, if you want to solve this in integers, then either C is plus minus 1, D is 0, or A is plus minus 1, B is 0. That's because the only units in Z root negative 5 are plus and minus 1. I should have put it under exercise 2 here. I'll modify that later, okay? So you can try and use Wolfram for this, but there's actually a really neat trick on how to do it using the norm map. But I really don't want to overcomplicate this with more definitions because there's plenty of them. So yeah, so maybe as long as you try solving this with Wolfram or maybe finding some kind of another trick, and you're good. So for exercise 3, what's the main observation that you need to make to prove that Z root negative 5 not a unit? You spoke already. Someone else. What's the main observation that we need to make? Remember, I want to convince you that prime factorization fails. Yes?
You need to find a number who has 2 prime factorizations.
Two different prime factorizations, exactly. And I can't manipulate one into another. What prime factorization did you find? Yeah.
6 is 2 times 3.
Exactly. Notice that 6 is, on one hand, it's 2 times 3, and on the other hand, it's
1 plus root 5.
1 plus root negative 5 times 1 minus root negative 5. Bam. 2 different prime factorizations. But, okay, I did not prove to you yet that FTA fails. I did not. Why? Because, well, remember, it's unique. Suppose that it does fail, okay? Suppose that FTA holds, okay? That FTA holds. Well, then these 2 must be the same factorizations up to multiplication by unit or permutation. Agreed? Well, then you agree that it must be the case that 2 is plus minus 1 plus root 5, or 2 is plus minus 1 minus root 5, which is certainly not correct, right? That's it. So, contradiction. So these are 2 different, so I just found you 2 different prime factorizations, okay? Just like that. Okay. So where are we going from here? All right, so I told you that there are certain rings where FTA holds, but there's only finitely many of them. Okay?
You only find it in any of them. There's like 7 or something. What do? Well, it turns out that you still can fix prime factorization. Need to develop more theory. Let's move on. We need to introduce the notion of an ideal. Okay? Ideal. Ideal is a non-empty set inside a commutative ring, which has 2 particularly nice properties. It's closed under addition on one hand, but also it has this interesting absorbing property. If you take an element in an ideal and you multiply it by any element in your ring, not in an ideal, it's not okay? Not an ideal, any element in your ring, then their product is still going to be in an ideal. That's the fascinating property of an ideal, okay? It absorbs multiplication by R, okay? All right. So let's see an example of an ideal. Again, so again, dry mathematical definition must be very difficult. You know, my eyes are just closing. I don't want to be here. But no, wait, it's actually not that bad. Here's exercise 4. Think about it just for 3 minutes. Okay, just 3 minutes. Prove that the set of all, okay, I'm going to give you an integer n, and I'm going to consider all multiples of an integer n. Prove to me that this is an ideal inside Z. Don't look at the board. Don't look at the board. All right, let's go. Let's take a look. Okay, again, it's really not that difficult. All that I'm asking you here is essentially do a Math 135 exercise. I'm asking you, here's a set. Verify 2 properties about the set, right? So I have two elements of the set, x and y. Show me that their sum is still in the set. Well, say, what does it mean to be inside the set? Well, it means that x is a multiple of n, integer multiple of n, and y is an integer multiple of n, okay? All right. Since, now I'm going to look at their sum. Okay, so x plus y is n times a plus b, but a plus b is an integer. So n is still a multiple, so x plus y is still an integer multiple of n. So it's in our ideal. Okay, so it's closed under addition. Now let's verify the absorption property, right? It's kind of strong if you think about it. I can take any element from the ring, and it's going to get absorbed under multiplication. Take an element x inside the ideal. R is any integer over here. X is an integer multiple of n. And I'm multiplying it by r, and it's still an integer. The result, rx, is still an integer multiple of n. So we see that rx is in n. Okay, is inside this ideal. So yeah, it's indeed it's an ideal, and you can pick any integer that you like, and this will be an ideal. Okay, here's the thing. Here's a question to you. Is z an ideal? The set of all integers? Is this an ideal? It is. It is. What's my n? What n should I take? 1, exactly. Or minus 1. Minus 1 also works, right? So yeah, so if you take 1, the unit, you get everything. In fact, and this sort of generalizes to arbitrary ring, a generator of your entire ring, and from that, in that sense, is a unit in this. Okay, let's move on. Exercise 5 prove that. I'm not going to ask you to do this one because I don't remember how to do it. It's not difficult. No, that's a false statement. It's not this. No. Okay, I remember how to do this one. It's not difficult. It's exactly the same thing as before. Okay, but but it's just the same thing, right? You just go and verify that indeed everything works out. Okay, this is indeed an ideal in z root negative. Okay, just takes a little bit more time, but you can do it on your own. Okay, let's take a look at the next definition. So now I'm gonna an example that we just saw in integer is called a principal ideal. Okay, a principal ideal, and it means that it's generated by a single element. Okay, so there's just one element that you take inside your ring, and everything is a multiple of that single element. Okay, it's not the simplest situation that can happen for ideals. Okay, it's being principal ideal. There's an exercise to prove that this other prime ideal that I've shown you in z root negative 5, this one over here, it's not a principal ideal. That's an interesting thing. There's no single generator there. Okay, that's what makes it sort of bizarre, and that's actually one of the reasons why z root negative 5 fails to be a EOD, but we're coming to that, okay? So I'm going to leave that to you, so think what it means to prove that this is not a principal ideal, okay? Maybe if we'll have time at the end, I don't know, we can think about this exercise. And now here's another thing. You kind of realize what I'm doing here. I'm going to define what a prime ideal is. So you can see what I'm doing. Before I was talking about prime elements, now I'm talking about prime ideals. And so I'm just sort of oversee what's going to happen is that, yes, the fundamental theorem of arithmetic will fail for elements, but it will still hold for ideals. Okay, so we're almost there to understand how to fix fundamental theorem of arithmetic. There's one element that is missing. I need to define how to compute a product of ideals. But we're getting there. Okay, so what is an ideal? What is a prime ideal? A prime ideal is an ideal where if you take a product that is of two elements that is contained in this set, remember P is just a set, right? Then either one or the other element must be in this set. Okay? Okay, so let's see immediately. Let's prove these two exercises. Now you do them on your own, okay? Just 3 minutes, think about it. Prove that 3 is a prime ideal. Prove that 6 is not a prime ideal. Okay? You can probably guess what prime ideals in Z are. Okay. Yes, go ahead. It's an inclusive order. Inclusive. It's one or the other. Could be both. Could be both. you may want to use Euclid's lemma if you remember this result from Math 35, okay? If a prime divides the product of two numbers, then it either divides one number or the other number. Right? So let's take a look. So for exercise 7, okay, so let's see. All that we need to do, definition, right? We just need to verify the definition of a prime ideal. Okay, it says, if I have a product of two numbers, A and B inside the ideal, then either one number has to be inside the ideal or the other one, right? So suppose that A times B is inside the ideal generated by number 3, the principal ideal generated by number 3. Then A times B is 3 times m for some integer m. So number 3 must divide A times B. But 3 is prime, so Euclid's lemma applies. So either 3 divides A or 3 divides B. If 3 divides A, then A is a multiple of 3. So it has to be inside the ideal. Okay? There you go. And the same thing, similarly, you can argue for the case 3 divides B. And let's take it by y6 is not a prime ideal. Who can tell me? Maybe someone who didn't speak yet? Yes, go ahead.
Because 2 times 3 is 6 times 1, but 2 is not 6 times anything and 3 is not 6 times.
That's right. So 2 times 3 is inside the ideal, but 2 is not in the ideal, and 3 is not in the ideal. So it's not prime. There you go. So 6 is not a prime ideal. That's it. Okay, so hope we understand that. So we're really close to understanding the fundamental theorem of arithmetic here. Okay, so this one I'm gonna leave it to you, prove that this is a prime ideal. Okay. So this is the definition of a product. It's exactly what you expect it to be. Okay, so just a collection of products of all the respective elements, and it turns out it's also an ideal. Verify that this is the case. All right, so it's, I didn't add it to a list of exercises, but it's a neat exercise as well. Okay, and so here's an interesting example. So if you take these two ideals, I and j, okay, these are both prime, then you multiply them together and you get the ideal 2. Just an interesting thing, okay? You can multiply ideals together just like that. And now we're almost there. All right, I promise, there's like very few definitions left, okay? Very few. So the ideal situation, haha, fun. A math plan here for you. An ideal situation is when, and the simplest situation that you can encounter, is when the only ideals that you have are principal ideals. That's the simplest thing that you can have inside the ring. Integers are like that. Gaussian integers are also like that. Eisenstein integers are like that, okay? But in general, it doesn't need to happen. And so then what mathematicians were saying, they were saying, okay, so let's us introduce, so there clearly could be something apart from the principal ideals, but how many things are there apart from principal ideals, right? And they define this clever definition of like equivalence class, okay? They say, okay, so two ideals are equivalent if I can multiply one by a principal ideal, another one by a principal ideal, and they're gonna be equal. I think I've forgotten something like, I needed to say that these are like non-zero and non-unit, right? Because otherwise it's kind of obvious, right? Under this definition. So I'll correct the definition eventually. But that's sort of the idea, right? And this is called an equivalence. So now we can see how ideals form equivalence classes. And it turns out that when you take a quadratic ring, the number of these equivalence classes is finite. And that's what a class number is. That's the definition that we were going towards, okay? That's the definition. A class number is a number that basically measures how many equivalence classes you have. No, it's not basically. It's exactly what it is. It's the number of equivalence classes under this specific, of ideals, under this specific definition, okay? So, now here's the thing. If age is equal to 1, then the fundamental theorem of arithmetic holds. It means that the only ideals you have are principal ideals. That's the situation in Z. You only have only prime ideals. You only have principal ideals. There are nothing but principal ideals. But when the class number is larger than 1, it fails. That's the meaning of this class number. Okay. Okay. So that's the main definition. Okay. Okay. Tell me if you want me to repeat something. If something wasn't clear. Okay. Go ahead.
Could you just go back to the previous slide?
Yeah, absolutely.
Need a couple.
Yes. So remember, I made a stupid mistake here saying that principal ideals, because you can easily take alpha and beta equal to 0, and then it's not very interesting. Alpha and beta equal to a unit, so it's not that interesting. So really what you care about here is that these are non-trivial ideals that you can multiply by, okay? Not a 0, not the whole thing, okay? 0 is sort of the smallest ideal that you can think about, and the whole thing is the largest ideal that you can think about, and everything is kind of located in between, okay? So I need to correct the definition. Good? All right, cool. All right. All right. The larger class number is, the more unique factorization fails in a quadratic ring. So remember this Z root -5 example where 2 times 3 is equal to, like there were 2 prime factorizations. Now imagine if you would go to somewhere where the class number is even larger, imagine like 10, 100, it actually goes unboundedly. That's a fact. Then you would see even more prime factorizations like that occurring. You know, like a single number can have like hundreds of prime factorizations, if any. Okay, so really far from being unique. So this is, so these are some examples, right? So in Z root -5, it's actually not that bad. There's only 2 equivalence classes, okay? It's actually not that challenging, okay? And so now I'm going to tell you the proper theorem that properly generalizes it's even more general than that, but at least for quadratic rings, I can formulate it for you. It turns out that if you take every non-zero ideal, which is not the whole thing, can be written uniquely as a product of prime ideals. That's the proper generalization. And it's the magnificent Ernst Kummer who discovered it in the 19th century. I think it's like 1860 something. Okay, that's around the time where he introduced these ideal numbers, and this theory was kind of developed. It originated with him, and then I think that eventually, I don't remember, maybe it was Dedekind who actually proved that one. So, but anyways, it's an old theory. It's like over 150 years old now. Whew, all right, I think that sounds exciting, okay? So we thought that fundamental theorem of arithmetic fails, but no, actually mathematicians are awesome. They managed to fix things. So now a little bit about this class number, because that's what I cared about in our research. We're kind of coming to the meat of what we're doing, right? So class numbers are hard to compute. It's a really difficult problem. If I give you a negative d, and I ask you find me a class number of OD, a negative square root, it's going to be hard. It's harder than RSA for sure. In fact, I think it was demonstrated that if you know how to compute a class number, you know how to do RSA problem. Okay, so it's at least as hard as RSA, probably even harder. Okay, but the quantum computer though can solve it. Quantum computer can solve it, but there is no classical algorithm for it yet. Tons of open problems about class numbers. There's Cohen-Lenstra heuristics, and I'm going to talk about it. Extended Riemann hypothesis, you probably heard about Riemann hypothesis. So if you want to generalize the Riemann hypothesis, there's many variations of it, but one of the most natural things that you can do is you can say, well, Riemann hypothesis is essentially attached to integers and rational numbers. And you can ask, well, is there a version of Riemann hypothesis beyond it? And the answer is yes. And you need to introduce ideals, prime ideals, and so on. You can introduce the Riemann zeta function on your quadratic ring, and so on, and so everything equals. So it's like Littlewood's bounds is an exciting thing because there's like this L function that analytic number theorists care about, and he proved certain bounds for this function that people really care about. But the problem is that it's conditional on the extended Riemann hypothesis. Okay, and so what mathematicians now would like to do is we would say, okay, so we would like to, okay, we can't really prove things. We can't really prove much about these things. Maybe we can provide computational evidence. Okay, computational evidence in support of all these amazing conjectures. Okay, so this is what we did. We computed class numbers for all negative d, such that the fundamental discriminant of this quadratic ring is at most 2 to the 41. So that's the definition of a discriminant. It's roughly d. So don't think too much about it. It's basically we're trying to compute discriminants, class numbers for all d up to some ridiculous bound. Okay. In our case, it was in our case right now it's 2 to the 41. So what we do is we want to provide computational evidence in support of things like extended Riemann hypothesis, Littlewood's bounds, and so, or maybe actually the other way around, right? Maybe we'll be able to disprove something, right? Maybe there's other conjectures that turn out to be wrong if you push d really, absolute value of d really far enough. Okay. Another interesting thing about it, and it's actually a very sort of proud moment, you know, because we already did this calculation to 2 to the 40 in 2016 with my colleague. I'll talk about it later. And then what we did is we posted all of our results. We posted them on this site called the Linear Modular Forms Database. Mathematicians use it to to some extent. And I'm so proud when people reach out to you and they're like, "Hello, I found your amazing data. Can you please tell me how to decipher it?" And I'm like, "Of course. You're an amazing mathematician with a Fields Medal. I can tell you about that." Okay. Yeah. So something like that. So mathematicians basically now they can use their data in their research. Okay. So that they can probably prove things about this. You know, maybe found counterexamples or something like that. So by computing these, we call it tabulation. By building these large tables, we're essentially serving mathematical community. Okay. So they can use it further. So now we're trying to improve our tabulation algorithm for class numbers. Okay, tabulation algorithm for class numbers. That's what we're doing. Okay, so I'm going to be very quick here. So this is deep stuff. And I don't know it. I don't know this stuff. Just to clarify, this all comes from the theory of like theta series that was developed by Kronecker in like mid 19th century, and then this whole theory evolved into what's called the theory of modular forms. It's a crazy area of mathematics, which I know little about, but basically what people discovered is that there are amazing tabulation formulas for class numbers. So these are two series which look very simple if you think about them, right? They're pretty simple, but if you multiply them in a clever way, you can start generating class numbers. It's bizarre. It's bizarre, and that's because it's like, oh my god, it's like this thing is a modular form of half integral weight, and it's that's something like that. So Don Zagier I think is the person who actually proved who proved a lot of amazing things about this. But though I'm pretty sure that this specific sort of generation formula was maybe known, it was probably known in the 19th century, definitely known in the 19th century. So yeah, so that's the thing. So you take series like that, you multiply them, and you're just getting class numbers of quadratic cubes. And there was only one problem, and it's a really big one. Where you can't generate class numbers for numbers of the form -8n minus 7. So for example, -7, -15, -23, for all of them, you need to come up with some kind of a different method of generating class numbers, and it's really slow. That's the bottleneck of our algorithm, okay? That's why our algorithm is slow, is because of this case, okay? But the other three, I mean, it's pretty amazing, huh? So let's do the quick exercise here. Here it is. So here's a Nabla series for it. It's actually not that difficult. Try it. It's very easy. It's an easy exercise. Trust me. Okay. So it's an easy exercise. Take this series. Okay. Take this series. Truncate it to q to the 4. Okay. So then compute its square and then truncate the square to q to the 4. Then compute the cube. Essentially, okay? So multiply square by a cube. So the reason why I'm doing it this way is because that's what our algorithm does it like this. We generate two polynomials of degree at post blah, multiply them out, and get another polynomial truncating it to the degree blah. Okay? So now try and do this. Okay, 5 minutes. I think we'll even have time to do some computer science. That's true. So excited. That's awesome. So remember, I'm saying series, but when you truncate it, it becomes a polynomial, right? At most of degree 4, maybe even less. If you use Wolfram Alpha, I won't judge it.
Or what you don't whoops. Plus 10 cubes. Yeah, okay.
No one just multiply it.
know that there is a simple solution. I should just like
I was gonna say.
turn off the screen fading, but yes.
It works.
It's too late now, huh? to do that.
Don't
All right.
sell. Still the next laptop.
Okay, did I screw up my computation somewhere? I was thinking I shouldn't have. No, I don't. All right. So, what's your result? Who got the result? Who got? Yes, tell me.
So for the first one, it's just 1 plus q plus q cubed. For the squared part, it is 1 plus 2q plus q squared plus 2q cubed plus 2q to the 4. And for the cubed, it is 1 plus 3q plus 3q squared plus 4q.
Sorry, 1 plus 3q
Plus 3q squared
plus 3q squared
plus 4q cubed
plus 4q cubed
plus 6q4.
q4. That's it. I don't care about anything else. Okay, so that's it. So I probably messed up my calculation somewhere. Help me to find my mistake. If you find time, if you have to. Okay, so modulo q to the 4. So look, I'm working modulo q to the 4 here. And essentially when I'm starting to calculate, I realize all that I need to do is I need to cube 1 plus q cubed. Cubed. And then when I start multiplying out, I notice that I can kind of, during my calculation, you can start getting rid of all the terms that have, oh sorry, 4, I need 4, oh my god, I do need 4. So I do need 4, but I don't need anything above 4. So I'm gonna get rid of it, and eventually I end up with this one, okay? And with this polynomial. So now let's think what this theorem is saying. It's saying that this divided by 3 is a class number of O negative 11. Why? Because if n is equal to 1, I have negative 8 times 1 minus 3, negative 11. So this thing over here, hope people can see it. No? Can you hear it? So this number over here, so it's 3 times 1, and this number 1 over here is a class number of negative 11. This one over here is a class number of negative, what, 17? 17, right? 19. This one I don't care about. Why? Because what?
The number won't be square.
The number won't be square free. It's what, 27 or something?
Yeah, which is 3 squared.
That's right. And this one is 35. So this is 3 times 2. So this is a class number of negative 35. So you can recognize, like, I mean, so again, remember the Stark-Hebner theorem, right? Class number 1, it wasn't the list. Negative 11 wasn't the list. Negative 19, class number 1, this wasn't the list. But negative 35, class number 2, this wasn't on the list. So fundamental theorem of arithmetic, classical fundamental theorem of arithmetic fails in this situation. In z root negative 35, but it doesn't fail. But it doesn't fail for ideals though. Okay, do we get this? Okay, so that's the idea of this calculation, and really that's what we're doing in our research. This is the CS part. Okay, so we're going to CS part. There's going to be even a CS exercise soon. Okay, so that it took only 1 hour and 50 minutes for a CS talk to get to some CS stuff. All right, that's what we're doing. We're just multiplying giant polynomials. We're talking like degrees 2 to the 36, 2 to the 37. Probably no larger even. I think so I think it's probably going to be even larger than that. So that's like what? 10 decimal digits in the degree. 10, 11 decimal digits in the degree. That's how big we're talking about. Okay, I can tell you a lot about. So the process goes like this. First, generate these 6 polynomials that I showed you before. Compute the respective the products, right? Somehow, right? You need up to this ridiculous degree. Truncate to a degree that you want. Read off the class numbers, save them to files. That's it. Okay, that's what we do. The question is, how do we multiply polynomials of super large degree? The answer is you use specialized C libraries. So if there's a Flint library, fast library for number theory. That's what it is, and it has like polynomial multiplication implemented, but it doesn't work to that scale. Like it doesn't work to that scale. If you want to, maybe you can multiply polynomials of degrees like 2 to the 25, 2 to the 26, but not beyond, maybe, well, I mean, so since 2014, maybe it's got, you can get to like 2 to the 30, but no way you can get to 2 to the 38 with this library. So you need something on top of it, and that's my master's thesis. Polymul, that's the library. So what it does out of core multiplication, because there's no way you can do everything in your RAM. At some point you need to save to the hard disk. That's what's called out of core. And then you need to use parallel computations, obviously, on a supercomputer. So you need like thousands of processors doing your thing. Well, okay, so I'm lying to you. So specifically for polynomial multiplication, you can get off with hundreds. So like we're going to be like 100 processors doing your thing. Okay? So that's how this is done. I can if you're interested, I can tell you more about like specifics how it's done, but I don't want to go too much into that right now because we don't have much time. So how does parallel computation work in here? For polymul, I was using OpenMP. Okay, so that's an API that you can have inside this. Your compiler, GCC compiler, can support this particular API. Okay, and then what it basically does is you have directives. You can say, hey, dear computer, could you please execute this block in parallel? This is like a for loop. Okay? Yes, I know this for loop has 1,000 iterations. Well, let 100 processors handle 10 portions of this loop. Does that make sense? That's what it does. So basically, there's kind of two paradigms. I'm telling you about one of them. This is OpenMP paradigm, and there's OpenMPI. OpenMPI is master-slave. There's like a dedicated process which tells other processes what to do. This is different. This is like, it's like one program that eventually forks. Computes in parallel, comes back and continues to work in a sequential mode. Then again it forks and so on, okay? So it's a slightly different paradigm for parallel computation. Moving on, so if you want to play around with OpenMP, once again, yes, go ahead.
So we shouldn't have like dependent data in the for loop, right?
That's right. So yeah, we're gonna play around with that. I have exercise for that. You're absolutely right. You need to be extremely careful when doing these parallel calculations. You need to make sure that you know where your local variables are, where your global variables, that everything is within the right scope, right? And there are certain portions where you just have to do you just have to do sequentially. A good example goes like this, like with polymul, it's like you were writing a lot of data on a hard disk, like a lot, right? But writing to hard disk is a sequential thing, right? And so what you basically need to do is you need to say, hey, dear process, if you reach this particular stage, writing to a hard disk, wait until other processes finish to the hard disk, so you basically line up. And then you write it, like you wait in line until you can write to the hard disk, okay? So then you can go on and proceed with your calculation. So it can get quite sophisticated. Our exercise is going to be quite basic, but it's more enough for you to get started with OpenMP. Okay, because really, with OpenMP, you don't need to know too much to get started. You don't have to install it on your computer. If you have it installed, that's awesome. For Mac users, I know how to install it. I'm pretty sure that it's easy for Unix users. But for Windows, I have no idea. Yeah. Yeah. So for Mac users, it's just basically installing. You just get Homebrew and install the latest version of GCC. That's what you do. Okay. You need to include this header file omp.h always in your code when you're using OpenMP, and then you need to compile with the -f OpenMP directive. Okay, always. And it's interesting, on the Mac you have to be aware that you always need to use this -11 or -whatever thing, because GCC on the Mac, at least the new Macs, is actually a shortcut for the native compiler, C-lang, and it doesn't support OpenMP. So just remember that. So you really need to remember. Okay, 10 minutes, and we can do some exercises. Okay, awesome. Okay, let me show you one basic, very basic example, silly example. Okay, so what do I do if I want to compute the sum of the first 8,000 numbers from 0 to 7,999 inclusive? Okay, I know that there's a formula for that, but I'm not going to use it. Okay, so I know it's silly, I know, but we want to practice OpenMP, right? So if I would remove this line, line number 6, and I would remove line number 1, that would be a standard C code, right? Just standard C code. All that is happening is I'm just adding this header file, and I'm adding pragma OMP parallel 4 directive. That's all it is. And that's it. So that's all that you need to do. At this point, as long as you compiled it like within parallel 1 and so on, what it will do is it will get here and it will say, aha, I have, okay, how many processors do I have? How many threads do I have? They call it thread. Okay, so I have 8 threads. Aha, let each thread handle 1,000 of each. Okay, 1,000 iterations. That's what's going to happen. And then you can see how each of them will going to be adding to this I. And actually, you would say that, oh, but I mean, isn't it weird that all of these processors will be saving their data into here? So it's safe. It's safe to do. Okay, this is not a problem at all. Okay, and it's done pretty fast. Okay, so this is not an issue. Now, so this is okay, so this is the output. So I'm just basically computing the, 7,999th triangular number. That's what I'm doing here. So let's remember this output, okay? So here are the 3 commands, very basic commands that you need to know. Get max threads just tells you how many threads will there be if I fork, okay? Set number of threads. You can increase the number of threads or decrease it, okay? And remember that number of threads does not always equal to the number of processors, right? You can have as many threads, but it's just that there's some complicated thing is going to go in the background where there's going to be essentially like, well, you know, you're computer science people, like you know these things much better than I do. And get thread num basically gets an ID of a particular thread. So they'll be given, say if you have 8 threads working, the IDs are 0, 1, 2, 3, 4, 5, 6, 7. That's it. Yes, question?
Can you go back to the compile code?
Compile code? This?
Like the command compile.
There it is. Yep. Yeah. Okay.
Thank you.
All right. You're welcome. All right. And finally, exercise. So here's an exercise for you. So here's what I'm doing. Pragma OMP parallel 4 is a fancy thing. Okay. And actually, it stands as a shortcut for something like that, where if you have a particular loop, it's going to dedicate for each thread with a particular ID. It's going to do something fancy to compute the results. So take a look at this code and tell me, what do you think the output of this code is? 5 more minutes. That's awesome. Yes. Okay. So remember the previous exercise, okay? And compare the previous exercise to this exercise. Sure.
Same answer as to exercise. We're just distributing the knots.
Aha! So now it says that it's the same answer. It's the same answer. All right. So look, I mean, if you think about it, what am I doing here? I'm computing in parallel, getting an ID, and all that I'm doing is I'm saying, okay, there's this many threads out there, T threads, okay, and I'm just computing a subportion. Just imagine if it would be like number 8, right? So thread number 0 computes from 0 to 999 inclusive. Thread number 1 computes from 1,000 to 1,999 inclusive. Thread number 2 computes 2,000 to 2,999 inclusive. Okay? Everyone is convinced? Okay? Okay, raise your hand if you got it. Okay. Okay? Awesome. All right, you're all wrong. This is incorrect. This is a bad code. Why is it bad? Tell me. Well, okay, so in this situation, okay, you're absolutely right. You're absolutely right, first and foremost, that this may not be evenly divisible. Let's say that t is 8. Okay, even if it's evenly divisible, what's the issue?
All the threads are trying to write to m in parallel?
Isn't that crazy? All threads are just fighting like for numbers I and m. That's the problem. M is not the local thing. They all keep writing to this m, overwriting the m. They all keep overwriting the I, and so on. So God knows what you're gonna get here as an output. I actually have it over here, like this code. Let me see. What is it? So GCC-11-F open NP, and let me get exercise. I think it's exercise 11, right? Is it 11? Yeah. Okay, let's see. Okay. Oh no, it's this one then. Okay, let's see. Okay, so now let's see what it's gonna give me. Crazy! It's just like it's gibberish. It's nonsense. It's ridiculous.
Race conditions.
You know? So it's just exactly race condition. That's the terminology. Yes. So that's the problem. That's why you need to be very careful when you're computing, when you're doing this sort of parallel calculations, right? And let's now take a look at the solution. So what's the solution here? Well, the problem here is that the variables m and I were sort of global for all of these threads. You need to make them local. So let's take a look at the code, at the solution that I have here. Here it is. Okay. So all that I did is I moved. Let me make it larger for you. Okay. So all that I did is I moved m in the scope of pragma and p parallel, and I moved I. I declared I in the scope of pragma and p parallel. So now m and I, they belong to this particular thread. Okay? It's not a global variable for them. You get what I mean when I say global, right? It's like everyone sees them. No. This is a local copy of m belonging to this specific thread. That's what it is. Okay? And that's a simple solution. And now it's going to give us exactly the right result. Okay? So need to be very careful. These are the kinds of things that we need to be thinking about when doing these sorts of parallel calculations. All right? So we're almost there. So I'm just gonna. I still have 2 minutes, and it's incredible, but I can actually finish this on time. So that's the answer. So just moving m and I inside. So there are 2 more exercises we can do. I know that we have this until 7, right? So I can hang out if you want. If you actually want to do this exercise, or you take it with you home and do it at home, and then eventually Naman and Bonnie will just send out the solutions if you like. So just do this exercise, but now generalize it. So what I mean by generalizing is, first write the code that accepts any positive integer k and computes the sum of k, and use pragma and p parallel 4, which is easy, right? It just does things for you. And then think, how would you do it without pragma and p parallel 4 and using only pragma and p parallel? Okay? It's a bit more sophisticated. You need to think, in particular, you need to think about the situation when it's not evenly divisible. That's the hard case. Like, what do you do if k is not a multiple of the number of threads? That's the challenge. Okay. So I'm leaving this for you. So in terms of the work in progress that we're doing, come on. Okay. So basically, we did this calculation in 2016. There's one terrible case, 7 mod 8, that we did not know how to handle. In 2020, this amazing paper by Brigman and Kane appeared, where they actually found amazing tabulation formulas. And we actually derived, from their tabulation formulas, we derived our new class number generation formulas that we hope will speed up our algorithms. So now we can cover, so remember, previously we would not be able to cover 7 mod 8. Now we can cover 7 mod 24 and 15 mod 24. But we can't cover 23 mod 24. But inside 23 mod 24, we can cover 23 mod 120, 46 mod 120, and 95 mod 120. And so my student Anthony is actually working on exactly that right now. So implementing these formulas, trying to tabulate class numbers, and we still don't know how to cover the cases 71 mod 120 and 119 mod 120. And that's like a really cool dissertation topic. Like if I would ask if I would get a chance ever in my life, which is improbable, to supervise a master's or a PhD student, that would be a great topic to investigate, like more tabulation formulas that would cover partially some of these cases, okay? Yeah, that's it. Here's some references for you, and thanks again for your attention. And if you want, I can hang out for a bit more to answer some questions, whatever you have, okay? Thanks. It is, right? It's crazy. It's crazy.
I don't know how much is going to stay in there, but.
Well, I mean, you know.